Okay, so we're going to take a look at the next section. So section 3.8 is on Newton's method. So the main question we're asking here is how can you find the zeros or the x-intercept of a function that you can't factor? So at this point in your mathematical careers, the only way that you know how to find zeros of polynomials is by factoring it and then setting it equal to 0. And then you set each factor equal to 0 and you figure out the x-intercepts that way. Now, maybe if you remember some specific things about pre-calc, you could use various other techniques of finding rational zeros. But even if we don't have rational zeros, we don't have any other strategy besides factoring to find the zeros. So Newton's method is going to help address this. So Newton's method gives us a decimal approximation. So we will not be getting exact values using Newton's method. We will be getting decimal approximations, and they're going to be, very long, but we're going to be wanting to use as much of the decimal as possible through this. Okay, and now just as a little note here that this is one of the techniques that calculators, computers use to approximate zeros. So if you've ever used the feature on your calculator to find the zero by just having it approximated to a whole bunch of decimal points, this very well Newton's method is behind the scenes to help us get to that point. So you are basically understanding how does a calculator find zeros without using something of factoring. So we're going to work through the intuition behind Newton's method for you to be able to see how does this work. But before we get there, I want us to remember this statement here. So suppose f is a continuous function on this closed interval a to b, where f of a and f of b have different signs. So one is going to be positive, the other one's going to be negative. Doesn't matter which one. Then there exists a point c or some value c that in the interval such that f of c is equal to 0. So basically if our function is positive, it is negative, then as long as it's continuous, there's some point in the middle that our function is going to be equal to 0. So the question is, why do we know this? So excellent. It's the intermediate value theorem. Exactly. So this is the intermediate value theorem. So the intermediate value theorem is what told us this. So what often is used before you start Newton's method is there even a 0 that we're looking for on an interval? If we know that there is a 0, then Newton's method is usually very valuable. But if we don't know that there's a 0, well then Newton's method is going to fail. It's not going to make any sense for us to do this. Okay, so I want to take a look at an example to help us get a feel of graphically what is happening with Newton's method. So what's going to happen with Newton's method is we're trying to approximate this value here. Now, if we're given just an arbitrary function of f of x is equal to something, right, we don't know exactly what this number is. So let's take a guess. We're going to do some approximation. So let's say, for instance, I pick this. I'm going to call this x1. This is going to be my first guess and say, yep, I'm trying to get to this point. I'm going to guess this is a decent number. So what we can do is we can figure out what is this point, right? I can plug this number into my function, and then I can figure out what the y value is. But because we're in calculus class, we now know a little something extra, right? We know how to find the equation of the tangent line at a point. So if we look at what is the tangent line at this point. So let's say this is the equation of our tangent line. Notice that this x-intercept is kind of close to this x-intercept, right? So we're like, oh, that's a better approximation. So this value here, I'm going to call this x2. So this x2 is a better approximation than my x1 was. But obviously, it's still not very good. So how can I improve this? Well, what if we try it again? So what if I look at this point up here? So again, I look at what is this point on the curve, and now I'm going to look at what is the equation of my tangent line. So my tangent line might look like this. And then again, what I look at and say, okay, this is a new x-intercept. This is kind of close to this x-intercept. So I could repeat the process over here. I look at the equation of this tangent line. I go over here and I get this, say, x4. I repeat over here, and then I look at this tangent line. I get this value over here. This is x5. So notice what's happening is that the more we repeat this process, we're getting closer and closer. So you can't even really tell eventually that you're going to be you're going to have these numbers overlapping. They're going to be extremely close to each other. So this is the idea behind Newton's method, is we're going to use the equation of tangent lines to help us find where this x-intercept or where this zero is of our function. So let's work through a little bit of the math of how can we generalize this process to use equations and use things that you're familiar with. So obviously the go-to thing that we need is we need to find the equation of the line, right? So if we use our point slope formula, we have y minus y1 is equal to m times x minus x1. Okay, general point slope formula, because obviously we're using the tangent line, we know what our slope is. So we know that our slope in this case is going to be f prime at, say, x1 times x minus x1. Okay, so we have this. Now, what we also know is that this point up here, let's call this, say, y1, this is the same thing as f of x1. So I could replace that over here. Y minus f of x1 is equal to f prime at x1 times x minus x1. So if I know what x1 is, I can find the derivative at that point, and I can also find the function value at that point. And this will give me the equation of a line because x and y are just arbitrary variables. But we use this tangent line for a specific purpose. We said once I know this line, I would like to figure out what is the x-intercept. So if we're trying to find what the x-intercept will be, well, we're going to find the x-intercept by setting y is equal to 0. So we have 0 minus f of x1 is equal to f prime of x1, and this is going to help us find our x2. So this number x2 is going to be our x-intercept. So what we can now do is solve for x2. Right? So we can solve for x2 by simply dividing by f prime. So this obviously goes to 0. I'm going to get a negative f of x1 divided by f prime at x1 is equal to x2 minus x1. I add this term over here. So I have x1 minus f of x1 divided by f prime of x1 is equal to x2. So this formula is exactly how we can now calculate what x2 is, using only information about x1. Now, notice that's just the first step, right? We said that over here, I have my x1, then I said x2 is a better approximation, but x3 was an even better approximation than that, and then x4 and x5. So what we can now create is this repetitive process that if we have x1 minus f of x1 divided by f prime at x1 is equal to x2, well, if we had to guess, how could we find x3? Well, we use only information about x2, we would have, this would be x2 minus f of x2 divided by f prime at x2. We're using the same idea, we have x4, so the next term in this is going to be found by taking the previous term and evaluating f of x3 divided by f prime of x3. And this can be repeated over and over and over and over again, as long as the derivative obviously does not equal 0. That's just a small thing we can't divide by 0, but that's much more for a later on class. So what this generalizes to is this formula for Newton's method that says f of x of n plus 1. So if I want to find the next term, this n plus 1 term in this, I'm going to use the previous term, and I'm going to subtract off f of x of n divided by f prime at x of n. And so this is our go-to formula for Newton's method. So we could do this by hand if we want, and we can calculate, let's say I start out with my first number is 1, I could plug this in and evaluate that, use that new number, and so on and so forth. But I said we're using decimal approximations, and decimal approximations, to try to keep a whole bunch of decimals around is going to be extremely difficult. So we're going to be using the calculators to help us be able to progress through this a lot faster. And so we're going to program the calculators to do this, and so I'll have a video about how we can use TI 83s or 84s to be able to work through Newton's method without doing it by hand.